I am happy to have Automotive Seminars as a sponsor for the show. Now, if you're not familiar, Automotive Seminars is a diagnostic technician training company. They've got a website that there'll be a link to in the show notes. And what they offer is top-notch training to technicians like us in the field. I've been taking their training courses for years and have got a ton of benefit out of it. They've got top-notch instructors, John Thornton, Scott Shotton, Scott Manna, and every other month they've got a 2-night course that you can sign up for. Join in, ask questions, and afterwards, you've paid for the course, you can access a recorded version whenever you want. You can rewatch the class 2 years later in case you wanted some details on it. And that is a fantastic feature. So make sure to check out the website to see what courses they have available and what's coming up in the future. This podcast is brought to you by Jarhead Diagnostics. Jarhead Diagnostics manufactures in-house diagnostic equipment and storage solutions, as well as distributes for companies like Pico, ATS, and TopDon. One of my favorite tools that I've bought from Brandon and Jarhead Diag is the case for the U-Scope. If you don't have a U-Scope, you probably should, but if you have one, you got to get one of these 3D printed cases, has a magnet on it, has a full-size BNC lead that you can connect to, and it gets rid of the weak point of that scope, which is the mini BNC connection, which is pretty fragile. This case makes this thing nice and secure and makes it an even better tool than it was. So check out jarheaddiag.com. The link is in the show notes. This episode is brought to you by L1 Automotive Training and Keith Perkins. If you're looking for education on module programming, J2534, EEPROM work, key and immobilizer, electrical diagnostics, or drivability diagnostics, Keith has a website, l1training.com, that's got over 60 hours of training videos on all those subjects and more. When I first started out doing mobile, I utilized Keith's videos on module programming in J2534 in order to get my head wrapped around what I would need for the tooling, the computers, the software setups, what kind of obstacles I would be up against when I'm out there programming modules on cars. And it was a huge benefit to me. And I continue to use the training videos that he has on his website. So I strongly recommend checking out l1training.com. We have got Auto Rescue Tools and Isaac Rodell as a sponsor for this podcast. Hey guys, if you're looking for programming laptops, you want the laptop set up ready to go for programming control modules on vehicles, you need key cutting equipment, you need diagnostic tools, Isaac is your guy. Has all that stuff available for purchase, and the support that he offers along with the purchase has been outstanding. I bought some stuff from him in the past. I got my Dolphin key cutting tool from him several years back. And again, the support has been phenomenal. Helped me out along the way with anything additional I needed to make it work for me. Also, for the month of June 2023, they've got Autel updates for sale. So make sure to check that out as well. Again, that's autorescuetools.com. The link will be in the show notes. Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping, and I will be your host. Today on the show, I want to talk about testing methods and test plans. As automotive technicians, repair technicians, diagnostic technicians, we use tests, a battery of tests, all the time, every day in just about everything we do to prove out a fault in a system or a faulty component or part to inform the customer what needs to be replaced or repaired in order to get the vehicle back into proper working order, right? And that's what we do, obviously. A lot of the time is we're trying to figure out what's broken on the vehicle, what's it going to take to fix it, right? How do we get to that point? We're going to use a variety of different testing methods in order to say for sure, yep, this is it. Now, the extent to which people actually utilize testing methods definitely depends on the shop, on the technician. You know, what level of accuracy are they really utilizing with their testing methods? And, you know, for me, not only performing a mobile diagnostic service for shops, but also working with students, you know, this is what I live and breathe every day is how can I make my tests more accurate? How can I add more tests to my arsenal? You know, can I create new tests that I haven't utilized before? Can I learn some new tests from other people, go to training and learn new testing methods, right? So I'm always absorbing this, but the goal for us as technicians is to have a variety of testing methods so we can prove something out. And, you know, we'll talk about this. It would be ideal to have 3 or 4 different tests that would prove out a single fault. And in some cases we can do that, other times not. But the more that we have and the more confidence we have in these testing methods, the more accurate we can be. And again, the more confident we can be in our diagnosis of a problem. And so I want to talk about this today. You know, if you've been doing this for a long time, you most likely do have a variety of test methods that you utilize every single day. But maybe you're newer to this. And again, I work with my students a lot and developing these test methods, and not only the methods themselves, but a plan to utilize them, you know, a logical path that you're going to take with these test methods is a big part of becoming a successful, accurate technician when you're going to be diagnosing problems. Because there needs to be an order to use these tests. And that's what a test plan is. We'll talk about that. And then each test we need to be able to perform and interpret properly. And that's where students get hung up a lot, is performing the test properly, number one. And even if they do perform the test properly, are they interpreting the results properly? And that's a, you know, big sticking point as they're growing their skill level. And I mean, we still run into it all the time, even as experienced technicians, if we're working with new systems, new components we're unfamiliar with, or maybe trying out a new testing method with some new equipment, we can run into some of these same roadblocks in our path trying to figure out what's wrong with the vehicle. So today I'm just going to give some general advice that I use with my students and myself to try to make my testing of these systems and components and parts as effective as possible and as accurate as possible. So first thing first, you know, let's define exactly what we're talking about by a test method. I think most of you can figure this out, but this will start us off down the path here. You know, I like to personally think about it as a way, you know, when I'm performing a test, it's a way to quantify or measure either a part, a system, or a component, and compare that to proper operation. Okay. So what I mean by that is if I have a battery and I measure the voltage, I would expect the voltage to be 12.6. You know, that's a fully charged battery. That's our known good. That's our reference. And I measure it with a voltmeter and it's at 10 volts. Okay. So obvious example, but that is a test that is going to quantify what's going on with that battery. Okay. It's discharged, you know, it needs to be charged and rechecked. That's what we're doing with our testing methods. You know, if we're measuring amperage in a wire, we're quantifying the electrons that are moving through that circuit. If we're ohm checking a wire, we're quantifying the resistance. If we're looking at data PIDs, right, we're relying on a lot to happen there, but we are quantifying what's happening, you know, with a running engine or a transmission or a wheel speed sensor, whatever it might be. We're putting a value to it and we're comparing it to, hopefully, we're comparing it to what would be considered normal or good. That's our test. And obviously that's going to take a lot of different forms, but that's what we're doing. And that, again, that's my personal thought, you know, when I think of what is a test, what am I actually doing when I perform a test? And there's a key part in there, of course, is we have to have the known good. And I'll talk a little bit more
about that as we proceed. But there was another definition as I was just writing up the notes for this episode that I came across on the internet that I thought was important to note here. It says that testing is the practice of making objective judgments regarding the extent to which the system meets, exceeds, or fails to meet stated objectives. Okay, so that's kind of wordy, but the one term in there, the one word in there that I wanted to touch on was the word objective. Okay, so it says the practice of making objective judgments. What objective means, if you're not familiar, you probably are, but if you're not familiar, objective means that it's not influenced by personal feelings and opinions. Okay, well, how does that come into play? And I know it's come into play with me trying to diagnose a vehicle where I allow maybe my experience or prior experience with that particular vehicle, system, component, whatever it might be, to lead me to believe I already know what's wrong with this car. I'm just kind of going through the motions and I know what I'm going to find because I've found this, 100 times before, or at least once before on this particular application. I've already got a destination in mind and I'm not necessarily letting my test results lead me to the conclusion. And maybe I'm doing a test and maybe I'm not exactly following the results the way I should because I have got a bias, a personal experience from before the last time I encountered this problem. And maybe I'm right. Maybe it gets me to the conclusion and maybe it's a pattern failure. It's the same thing I saw before, but maybe it's not. Maybe this is unique failure and I'm wasting my time by not following my test results, by not using those, quantified values I've got from my test results to lead me in the right direction. I'm going off of personal experience and things I've seen before. And again, it's not to say the experience is a bad thing. It can get us to the solution pretty quickly. And sometimes we've got that gut feeling where I know what's going on here. And a lot of times we're right, especially experienced technicians. But I still, and I struggle with this, but I still try to utilize proper test results to lead me to that conclusion without skipping ahead to anything, because sometimes it works, but sometimes you end up wasting time that way. So I just thought that bringing that up based off of that definition was important to note before we get in here. Is the whole goal here is really using the results we're getting from our test methods to lead us to where we need to go. And if we do that, we're effective in that, we should always get to the solution. Of course, there's real life, there's variables. We'll touch on some of those as we continue. But the bottom line is, with the test, our goal is to determine if a part, system, or component is functioning correctly or not. I mean, we really boil it down, that's what we're looking for. Can this wire supply current? Can this motor turn this engine over? Can this injector spray fuel, right? Can this coil spark? That's what we're doing. We want to know, does this part function the way it's supposed to? And our tests are going to prove that. So I've got 3 particular items that I wanted to cover in relation to testing methods and test plans. And the first one, I think this is probably one of the more important ones, is, and I've talked about this before as well, probably talk about it again at some point or another, is really having a good understanding of how that system, part, or component works normally if there was no issue, right? And sometimes this is really obvious, right? If we're talking about an engine and it's got a rod knock, obviously we know that that's a bad thing. If an engine comes in running and we hear a rod knock, okay, this is a serious repair. There's major damage to this engine. And I don't think it takes a whole lot of skill or testing, besides listening to the engine, to confirm that, yes, there's definitely an issue here. But that is only because we've heard thousands of other engines run normally. We know what the standard is. That noise only stands out to us as technicians, or most people probably, because we know what normal is, what normal operation of a running engine sounds like. Now, sometimes this isn't so easy, because as we get into really detailed testing and intricate, complex systems and components, maybe with things that aren't visible or audible. We have to use test equipment and techniques in order to quantify something. This gets a little bit more difficult. And if it's a new component, system, part, vehicle, engine that we're not familiar with, we may not be so confident on what normal is, looks like, sounds like, measures at, right? And we run into this all the time, especially if you work in the aftermarket world. Odds are you're seeing cars and systems and components that you've never dealt with or dealt with once in your career. And now you need to make the assessment when you're doing your test is, well, what is normal operation, right? What would this component or system look like if it was performing properly? And again, I understand that sometimes that's easy, right? This engine is misfiring and it shouldn't be misfiring. It should be actually completing the 4-stroke cycle. I understand that. But when we get into our testing of components, maybe we're not familiar with a direct injection fuel injector, right? We're not familiar with the waveform or the operation or the drivers or the circuitry, and we don't know what normal would look like. We don't really know how we would quantify a measurement to that system if everything was working the way it's supposed to. And that's going to make our test, well, that might make our test useless. And I would say if you're unable to determine, what normal looks like for a particular test method, the test is going to be useless. And that's a big part of this, part of any test that you perform, whether it be electrical or with the scan tool or mechanical of some sort. If you don't have an expected result, if everything was working normally, I wouldn't bother performing that test. And I know I've been guilty of this before. I'm doing a test on a system or a component. Maybe I've never tested this system or component this way, or I've never dealt with this particular application before. And I'm performing a test. Maybe I'm even familiar with the test itself. I'm measuring amperage to something. I'm looking at an amperage waveform on something. I'm familiar with the test. I know how to put my amp clamp around something and set up my scope, but I don't know what I would expect to see on the screen as a waveform if everything was working normally. So is that test going to be useful to me in that moment? And it's really not. It's going to be less than useful if I don't have an expected result if everything is working normally. And it's a big part of testing that we got to remember as we go into these things is, what's my expectation if everything's fixed, working the way it's supposed to? And I invite you to challenge yourself, not only to find what that normal is, and we'll talk about some ways that you can do that, but also to really understand what your result means. I mean, even if you know that when you ohm check a CAN bus network, for just example, that you're supposed to get 60 ohms. Okay, great. And we know that that's normal in that application, but I invite you to go a step further and ask yourself, why is that normal? Why am I seeing 60 ohms when I ohm check the network? Well, there's 2 terminating resistors wired in parallel, right? So that's going to add something to the value of that test, depending on the application, right? It definitely depends on the network structure, but let's say we're working on a GM and we see that we got that 60 ohms. It means that everything is plugged in. All the modules are plugged in, connected end to end. Because if one of them becomes unplugged, you are going to lose the terminating resistor on one side of the network, right? So anyways, I'm not trying to get into GM network stuff here. Just an example of why do we see our known good value? What does that mean to us? Because if we really understand, not only is this value correct, is it normal, but why it's normal, we can be very confident either moving to the next test or making a diagnosis with the system. It's not just taking the value from the flowchart and saying, okay, well, my value matches the flowchart, I'll move on to the next one without really thinking about it. We want to actually interpret these values that we're getting from these test measurements into real life, into why does it measure that? Why is that normal for that particular application? Now, of course, the CAN bus example is a very, easy thing to understand why that's a normal reading. Sometimes getting those normal readings isn't that easy. Sometimes the answer to what's normal, what's a known good, isn't quite so easy. And the example I would use here is something like an intake or an exhaust pulse waveform, right? So we're using a pulse sensor, we're going to use a scope, and we're going to crank the engine over, we're going to start the engine, and we're going to look at the pressure pulsations inside the exhaust and the intake. And I've talked to a few people on the podcast about this before. There's lots of training on this out there, but it can be a challenging test method to use to say that, yes, this particular application is good, this is a known good, and this application, or, this time I did the test, this is bad, there's a problem with this engine. Not to say that you can't with the proper training, but I'd venture to say that it's not quite as easy to interpret those test results as compared to something like ohm tracking CAN network, right? There's going to be some training, some experience, some trial and error, some experimentation in order for you to be able to say for sure, yep, I recognize something in this waveform. Or you're going to need to be able to see a number of known goods before you can confidently use that test method to call a problem on a particular car. And this is where the research and experimenting and intentionally seeking out known goods, taking the time yourself either to network or taking the effort to actually find, create, measure these known goods yourself on good working vehicles. Of course, this is going to take time out of your day in order to do this, but that's what makes these testing methods more powerful when you actually need them, right? Because now you've messed around with this. You've played around with that pulse sensor in your driveway on 3 or 4 cars, and now you can take that knowledge to the broken car that you see in your bay on Monday, all right? And if you hadn't done that, yeah, sure, you got the pulse sensor, you got the scope, you got the whole setup, you know how to set it up, you know how to perform the test, but you don't know exactly how to interpret that result because you don't know exactly what known good looks like. So there's some effort there to make that valuable in a more complex testing method, right? Some of the easy ones, I get it. We're measuring battery voltage or something like that, or maybe measuring compression of a cylinder. But heck, even that, there's so many variables in that, good compression on one engine is not good compression on another engine. I mean, we see ranges from, just shy of 300 PSI in some extreme cases to just over 100 PSI in some other extreme cases. It depends on the engine, the application, the age of the vehicle, what is good, right? We can perform the test, but if we don't have that known good for what we are working on, it makes the test less valuable or maybe not useful at all. So that's my first big point. I know there was a lot in there, but it is making sure that we understand how the system or component works and having an expected test result if everything was working normally. We're going to compare our actual test result to that expected result and hopefully make a confirmation. Is this system, component, or part working the way it's supposed to or not? So the next point that I wanted to make feeds off of that a little bit, and this is understanding the limitation of our chosen test. Every test has its purpose, but each one also has a limit. It can only tell you so much about a system or component. And it might be exactly what you need for that particular application. One test might be all you need, but sometimes we can read too far into just the one test that we're performing. We put too much weight on one simple test. And I know I've been guilty of this before, is interpreting a test result and putting too much value in it and making a call based off of that, when that I was just really latched on to this one thing that I saw that I thought was bad, but as it turns out, I was misinterpreting that data or that test result, and there was something else going on. For example, I used to use the blue block tester fluid for detecting combustion leaks in engines when I worked at Firestone. That was kind of our go-to for detecting head gasket problems, right? You get some weird overheating problems or coolant consumption or something like that, where it's not a real obvious head gasket leak. There's some symptoms maybe, but nothing that really gives it away. We would use this block tester fluid. We put it over the radiator neck. We'd run the engine and we'd squeeze the little ball. It would pull in vapors from on top of the cooling system, and it would go through a blue fluid that you poured into this little tube. And I'm sure many of you have seen these or possibly used them. And if there was carbon monoxide present, it would actually change the color of the fluid in the tube from blue to green to yellow if there was a lot of carbon monoxide. And you can try this just by putting it in the exhaust stream, and it will change yellow almost immediately. Well, if it changes to yellow based off of the vapors in the cooling system, there's carbon monoxide present in the cooling system. Where's that going to come from? Of course, the combustion chamber. So you have some sort of combustion leak, whether it be a cracked head or a head gasket. Take it apart and figure it out at that point. But here's the deal with this test, which I'm sure many of you know. It's not the most reliable test. Now, if it fails, sure, that means you definitely have some sort of combustion leak. No questions, right? As long as you really didn't mess up this test, maybe it's there's a high level of carbon monoxide in your shop. Hopefully there's not. It's going to be pretty reliable if it fails, if it turns yellow. You definitely have a head gasket leak. But just because it doesn't turn yellow, that does not mean that you don't have any type of combustion leak. And I ran into this many times, which is what led me to stop using, well, I wouldn't say stop using this test, but stop putting so much weight on this test, right? It's one of those things. If it fails, it's failed. There's a problem. But if it doesn't fail, well, there still could be a problem. This isn't enough. We can't put everything on this one test, right? That's the point of this. And again, simple example, and there are other ways to confirm whether or not there's a combustion leak. Maybe we could use a gas analyzer if we have access to one in the same method, but it's going to be a more sensitive test, right? And we can also look for hydrocarbons in addition to carbon monoxide in the cooling system. Maybe we could use a pulse sensor. I was mentioning the pulse sensors before. There's videos out there on YouTube of guys connecting the pulse sensor to the top of the radiator or the coolant reservoir and cranking over the engine using an ignition sync in order to figure out, is there a pressure pulsation coming through into the cooling system that would represent some sort of combustion leak, right? And there's various other methods, but that's where I'm getting with this is we don't want to just single out one test and say this is the end all be all to determine whether there's a fault in this system or component. And again, maybe in some cases that's all you need, but in a lot of cases we need more than one testing method. And this is what I like to have and seek out more than one testing method for a specific problem. Even if the methods I have are pretty effective, I'd like to know another way to test this system or component. What else can I do to be that much more confident, right? If I could have 3 different ways to test the same problem and they all come up as, yep, this is the issue, I can be very, very confident in whatever component or part that I'm calling, that I'm making the diagnosis on. Yep, I tested this 3 different ways and they all say this has failed. Okay, and in a perfect world, we'd have that. I realize that that's not the case all the time, but it relies on us going out and seeking out these new testing methods, new equipment, different ways of doing things or looking at things, going to training, networking with people. That's how we discover some of these things. And again, that goes back to dedicating some of your time to develop your test methods. So the only way it's going to work is you've got to be able to commit yourself and commit some time to having that arsenal of tests available to you. All right. The third point that I wanted to bring up for this was, and this might seem obvious, right? Especially for experienced technicians, but heck, I run into this all the time, is asking ourselves, are we performing the test properly? And it seems obvious, but so many things can happen during testing that creates false test results, right? Maybe we know the test to do, we know exactly what we're after, but something happens where we get a result that is not accurate, right? It's not really what's happening on that circuit or within that component because something wasn't set up correctly, or maybe something's broken with our testing equipment. Just a simple example that happens quite frequently with students is when we connect a test light to battery negative or ground of the vehicle, and then whatever we touch with the other end of the test light should light up the test light if it's positive battery voltage, right? Well, what if the connection to the ground or to the negative battery is not good? Whatever you touch with that test light, even if it is battery positive, it will never light, right? So a very simple example of performing a test improperly, setting it up improperly, not making that good connection, and maybe getting a false result if you didn't realize that you did that. Okay. Again, a simple example. Most of us can overcome this. You know, I always touch the test light to battery positive to make sure that everything's good. Well, heck, I've had the bulb go out on my test light. I'm like, what the heck's going on? Of course, just replace the bulb. But anyways, sometimes this is not as simple as a test light, right? I mean, this can be things like setting up the vehicle options incorrect when you enter the information into the scan tool, right? We're connecting to a vehicle and I didn't enter the vehicle options or the engine size or some value correct as I'm building the vehicle in my scan tool, and it doesn't allow me to connect to the module that I need to, or allow me to perform the function that I need because I entered something incorrectly on the scan tool. And of course, this is all user error, right? This is things that we're doing that give us false results. And we got to be aware of that. But sometimes it's also equipment failure, right? Sometimes it's not exactly our fault. You know, I've had test leads for scopes and meters that would actually open up internally, and that happened on the U-scope, and I had to get a new lead for it. But while it was happening, it was really throwing me for a loop because I was getting all kinds of weird patterns on the waveform because the lead would open and close, and I thought it was in the circuit, but it was really in my scope. And that can make for a really frustrating diagnosis if you don't realize that it's your equipment that's having a problem. I've used scan tools on vehicles, aftermarket scan tools that actually caused communication codes to set within the vehicle. And of course, the one I was there for, of course, I was after a communication issue, but the scan tool I had was causing more issues on top of that had me chasing my tail for an hour at the very least. Now, again, you know, it's equipment fault that's causing these problems, but we got to be aware that that stuff can happen. So if you have anything weird happening when we're performing these test results, you just always want to ask yourself, is my equipment working the way it's supposed to? I actually had a wire piercing probe recently that also opened up internally, and no matter what I did, I couldn't make contact with this wire that I was trying to, and it had me thinking that the circuit was at fault. Well, it was my testing equipment. So we always need to consider that, you know, we got to test our test equipment as well to make sure that it's working the way that it's supposed to. So maybe that's taking a step back and actually performing a test on our equipment beforehand, just making sure, okay, yep, this definitely works. I can use it to actually diagnose the real problem on the car. So again, those are my three main points: is to understand how a system works normally, to understand the limitation of each test method that you're using, and to ask ourselves, are we performing the test properly? And again, that could be our fault or the equipment's fault, but is the test being performed properly? Because if we get false results that way, we can't use it. So let's take all that and wrap this up, put this together. How do we use this when we create a test plan? Well, what is a test plan? I'm sure you've heard this talked about quite a bit. You know, it's terminology that's used I feel like it's used more often within European service information scan tools. They talk about this is the test plan that you're going to follow. I like to create my own test plan, but really all this is to me is a series of testing that I arrange in logical order in order to diagnose something. One example would be like a misfire, right? I go to a vehicle and I'm trying to diagnose a misfire. The first test that I might perform is, well, I might verify the concern, of course, but I'm going to check codes, right? That's performing a test on the system to see, can we zero in the cylinder? Or do we have misfire counters that I can look at, putting a value to each cylinder and how often one is misfiring compared to the other. Of course, we know what good is there. We want to see zero, and if it counts up, we've got a misfire. And then building off of that, it will then determine what is my next test, right? So we got to take everything into account to perform a single test, but now we want to move on to another test, right? Because some tests are going to be general in nature where they just tell you if you have a problem, but not exactly where it is. But each test is going to build off of the other one. And so, after I find out, okay, cylinder 1 is misfiring, what I might do is a relative compression test, right? Let's eliminate mechanical engine problems. And I might just do an audible relative compression test. Let's listen and see, do we have a dead hole on this engine, right? Now, I know in my head what an engine is supposed to sound like cranking because I've heard one crank without starting many, many times. And I can pick out a low compression cylinder. As long as there's a significant drop in compression, I can pick that out just by listening to the starter. If I hear that, I'm going to move my testing towards some mechanical, right? So maybe I'll do a relative compression with a scope at that point. Maybe I know the cylinder, so I'm going to go in cylinder and I'll look at the pressure inside that cylinder. Maybe I'll do some sort of pulse waveform with the exhaust or the intake, right? And those tests are going to give me more detailed information on what's going on with that engine, right? And each test is going to have an expected result, right? Now, in this case, maybe I'm expecting to see low compression, but I know in a normal running engine, there should be X amount of compression. Well, this one only has this much, right? And I'm looking at my in-cylinder pressure waveform, and I've been to several classes for in-cylinder pressure waveforms, so I have something to compare it to. I know what normal looks like. Now, we got a question though. Is normal for this engine the same as another engine? And it might not be. So we got to be careful there, right? There's so many variables that we got to consider, but maybe I've taken the time to get a known good from this particular application. I have that stored in my data on my laptop, and I can pull that up and compare it to it. And I can say, okay, here is the issue. This valve is leaking, or this cam lobe is worn out on this particular cylinder for sure, right? That's one path that my test plan might take me. Maybe the relative compression is good. I move on to spark, or I move on to fuel. And each one of those is going to have more detailed tests based off of what I find, right? Each test is going to lead to another, and this is a test plan. Now, I realize that most of us, if we've been doing this for a while, if we're experienced, this is kind of intuitive, right? We don't always really think through this. It just sort of comes to us, right? We see something, we get a result from a test, and we know exactly what we're going to do next because we've seen all of this many times before. But where this becomes important is when you're tackling a problem or system or vehicle that you're not as familiar with, or maybe it's just a really challenging problem, which we all run into from time to time. Having a method to kind of sit back and organize your thoughts is really going to help you get to the solution more effectively. And that's really what the test plan is. And the reason I went through the misfire is just to show you that we kind of do this already, even if we're not aware of it. We move through the steps in a logical process, and hopefully you do. If you don't, that's something you can work on, right? Students need to work on this because they don't have that that logical path. I need to do this test because of the results of the previous one. They might start jumping all over. They might start just, okay, I'm going to look at fuel, then I'm going to look at spark, and not really sticking to a path or a funnel like Jim Morton says, right? But when we get a challenging problem that it's not so intuitive, we don't exactly know where to go, this is where sitting back and actually writing out a test plan, writing out some steps you're going to follow can be really beneficial. And I had the students do this, and I do it myself when I'm presented with challenging issues, which I seem to get plenty of the time. I'm challenged often. I'm working through one right now that hopefully will make it onto the podcast in the near future, as long as I can figure it out. But it's been very challenging, and I had to sit down with a piece of paper and write out my test plan. Okay, if I see this, I got to go here. If I don't see this, I've got to go this direction. I've got to do this test. I have it all written out on a yellow legal pad. And I suppose you could do this all digitally too. I like writing stuff down with a pen and paper. That's just my style. But having that test plan together and taking into consideration all the things that we talked about with the actual tests themselves, this can all make you more successful, more accurate, more efficient in diagnosing problems on vehicles. So I'm going to wrap it up right there. I've talked about this long enough. Hopefully you got something out of this. But other than that, let's get out there, start fixing the world one car at a time.